So in this video, we're going to talk about ways to draw organic molecules. So several different representations. The first one is just structure's molecular formula, which is how we really wrote everything in general chemistry. So when we're talking about its molecular formula, we're just giving the atomic symbol for the atom, and then after it, a subscript telling us how many atoms, I guess, of that element we have. So if I wrote C2H6, that would be its molecular formula. We could do CH3O, C5H12, all of those would be the molecular formula. It doesn't tell us anything about the structure of that molecule. It only tells us what type of elements, right, are present, or which elements are present, and then how many atoms of that element we have. So it doesn't give us a ton of information about that molecule. I'm going to draw one more. We could do C2H6O, right? Again, you know, it tells us nothing. Are the two carbons in a row and then that's bonded to the oxygen, or is it carbon, oxygen, carbon? What does it look like? We don't know. Again, all we know is what types of atoms we have and how many of each type of atom we have. The other type are structural formulas. And structural formulas are what I've been drawing mostly so far. So it's where you're showing every single bond. So the C2H6, if I draw out those two carbons and then I put the hydrogens on them, right, that would be considered its structural formula. We can draw what's called its condensed formula. And the book uses a lot of condensed formulas. So you've probably already noticed this. As you're going through the homework, you've probably encountered this one, and then the fourth one that I use a lot. You've probably come across it already too. So what we're doing in the condensed formula is we're kind of combining the molecular and the structural. So what we're doing is we're taking the carbon, and then we're saying how many hydrogens or what's bonded to it. We're representing that number of hydrogens by a subscript. The easiest way is to just take this one I just drew and turn it into condensed. So the first carbon, and then that carbon is directly bonded to 3 hydrogen. So I'm going to write CH3 because I have 3 hydrogen bonded to that carbon. Now I have another carbon. It's bonded to 3 hydrogen. So I'm going to write CH3. So that would be the condensed formula. We know the hydrogens are not between the carbon and the other carbon because hydrogens can never be in the middle, right? Hydrogen can only ever have one bond. And by the time we get to organic, we know that. So there's no way, you know, if you were in 130, it would be easy to interpret it as this. But we know that's completely impossible, right? The only way that could be put together is if the 2 carbons are bonded to each other. So we can write it that way. If you have other atoms, so let's say that I have this structural formula. Let's actually put an oxygen in the middle. Let's make that an oxygen. And then that's bonded to 3 hydrogen. If I wanted to write this in the condensed formula, again, I have carbon with 3 hydrogens on it, so CH3. Then I have an oxygen, and then I have a carbon with 3 hydrogens on it. So that would be its condensed formula. We could have something that has branches. Let's do 3 carbons in a row. And then on the middle carbon, I have another carbon. And then to give everything its 4 bonds, those all have hydrogens. This is, of course, the structural formula I'm drawing, right? Not the condensed. So if I wanted to write this one, again, I have CH3, And then I have a carbon, and then that carbon only has one hydrogen on it, so CH. It also has a CH3 group attached to it. And I can draw that up or down, it doesn't really matter. I'm going to draw it up because on my structural formula it's up. But again, you could draw it down, it doesn't matter. So that middle carbon is bonded to a carbon that's bonded to 3 hydrogen and a hydrogen. And then I have my other carbon, my last one, which is bonded to 3 hydrogen. So that would be my condensed formula for that. The last one, I call them skeletal formulas. They go by a couple different names, but this is the one we're going to use. This one looks really weird at first, but I promise you, you will learn to like it. It's so much less work than the other ones. So what we're doing with skeletal formulas is that carbons are represented as the end and intersection of lines. I don't actually have to make a C. I'm going to have the end of a line or the intersection of lines, and I'll show you what I'm talking about here in a minute. Hydrogens that are bonded to carbons are assumed. We don't have to show them. So hydrogens bonded to carbons are assumed. And then all other atoms are shown. So carbons are represented as the end and intersection of lines. Hydrogens bonded to carbons are assumed. We can count to 4, right? Or whatever we have to count to depending on its formal charge. And then all other atoms are shown. So let's do it with this example first, because that's probably going to be the easier one. So I have 3 carbons in my main chain, right? Going across the middle here, I have 3 carbons. So those 3 carbons are that. And I know it looks kind of weird at first, but I have a carbon here, it's the end. I have a carbon here, it's the intersection of those 2, and I have a carbon here. So that's 3 carbons. And then on the middle carbon, I have a carbon. So I'm just gonna go up to that one. I could have started, like I did a zigzag up. If I wanted to do it this way, that's still 3 carbons. 1, 2, 3. But then the middle carbon, I would actually draw it down because we want to try to keep the geometry, right? If I would have done that and I would have done it here, I now have these super crazy tight bond angles. So don't do that. So if you're going to put a branch, that one's upside down. If you're going to put a branch on something and the point is up, the branch goes up. If the point is down, then the branch goes down. And then if we go back and we look, let's just count hydrogens on here. So I'm going to look at this very first carbon, the one on the left. So I'm going to look at this carbon here that I just made pink. It has 1 bond already, right? This one. It doesn't have a formal charge, so I know it has to have 4 total. Since it already has 1, right? 4 minus 1 is 3. There's going to be 3 hydrogen on that carbon. If I look at the middle carbon, it has 3 bonds already. 1, 2, 3. It doesn't have a charge, so I know it has to have 4 bonds. So it's going to have 1 hydrogen on it. And if we go up and look at this structure, there's 1 hydrogen on that carbon. If I look at this one, it has 1 bond already, so 3 hydrogen. This one on top has 1 bond already, so 3 hydrogen. If I wanted to draw the skeletal structure of this one here, let's just do it up next to it. I have an oxygen in the middle, and oxygens are going to be shown, right? All other atoms are shown. So I'm going to have this. That's how I'm going to draw that one. You could totally do it upside down, but that's how we're going to draw that one. Right, so I have a carbon here. it has one bond, so it has 3 hydrogen on it. I have 1 carbon here, it has 1 bond, so it has 3 hydrogen on it. Since we can count to 4, we don't have to actually draw them. So that's how I would draw that one. There are 2 lone pairs, I didn't put them on there, but there are 2 lone pairs on that oxygen in both of these. And we know that because it's not charged, right? If those lone pairs weren't there, it would have a formal charge. So once you guys get used to formal charge, I often don't include lone pairs because I assume that you can figure it out based on the charge, right? Before I put those on there, I had 2, 6 being my number, right? My number of valence electrons. So to have no charge, I have to subtract 6 from 6. So I had 1, 2, and then there has to be 3, 4, 5, 6. It's the only way it works out. So you do want to be starting to get pretty good at determining whether or not something has lone pairs or not. So let's do some where I give you a skeletal structure, and then we have to go backwards. Let's put a nitrogen in here. Actually, I'm going to leave lone pairs off too. And then you guys can tell me how many it has. Let's put a double bond, and we'll put an OH group. Okay, so my skeletal structure. And what I'm going to do, I think the easiest way, since I don't have you in front of me pointing stuff out, is I'm just going to convert it to structural formulas so you can kind of see what's going on. So the carbon on the very far left, it's bonded to the carbon in the middle. That carbon is bonded to an OH group, which means the carbon on the left has to have 3 hydrogen on it. This carbon right here, right, has a bond to this carbon, a bond to oxygen, a bond to the carbon on the left, so it has to have 1 hydrogen on it. My oxygen has 2 lone pairs because it doesn't have a formal charge. This carbon has a double bond to a carbon, right, the end of a line, which means it has to have 2 hydrogen on it, otherwise it would be charged, and it's not. That goes to a nitrogen, which has hydrogen. That goes to a carbon, which goes to another carbon. So this has 2 hydrogen, and then this has 3 hydrogen. And then nitrogen, 5 being its number of valence electrons, it has 3 bonds right now, so 4, 5. So if I was to draw this out structurally, I would get something along these lines. But drawing this is just way quicker. We could have rings. If I do this, I have a ring of 6. So each one of these intersections is a carbon. And then each of those carbons is going to be bonded to 2 hydrogen to get its 4 bonds, right? None of them are charged. Be careful with triple bonds. Let's put a halogen on there. What haven't we done yet? Let's do a double bond to oxygen. So I'm just going to count carbons first. So there's a carbon here, a carbon here, a carbon here, 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 and then there's one here. Remember that triple bonds, right? That carbon, the last one I just put the highlighter on, is sp2 or sp hybridized. So it has, it's linear, right? It only has 2 electron groups, so sp. And then I have a carbon here. So just if I draw that triple bond without the rest of the molecule, a lot of times people miss that there's a carbon here. Because those bonds are stopping, right? They're not going all the way to the end. There has to be a carbon. You don't have bonds that go part way between 2 atoms. They go all the way from one atom to the next. So there has to be an atom there. So watch out for that. That's the more common mistake when folks are learning. And then if I was to put the number of hydrogens on here, I'm going to get lazy on you. I'm not going to put hydrogens, I'm just going to put lines, but you would actually have to put hydrogens. So I guess there's 3 on there to get 4, right? I guess I will put hydrogen. There has to be 1 here to get 4. This carbon here has 3 bonds, so it has 1 hydrogen. This has 2 hydrogen. Again, we're just counting to 4. This one here, no hydrogen, because it already has 4, right? 2 single bonds and a double bond, right? It has its 8 valence electrons. Might be the better way to think about it. This carbon here already also has 8 valence electrons, a triple bond and a single bond, so no hydrogen. This one has 1 hydrogen. So that would be this one. I know it looks kind of weird to begin with, but really it's so much nicer once you get used to it. So I would definitely do some of the practice problems on these. I'm rarely, I'll draw out structural formulas if I'm trying to make a point. Molecular formulas usually will be given as part of the problem, but I'm never going to really ask you to draw one. Condensed, the book uses a lot, basically because it's easier to type this than it is to draw one of these molecules. This is what skeletal is what I'm going to use pretty much from here on out. So please start to get comfortable with it. It will get better if it looks kind of weird to you at first, I promise.